In this video, we'll look at two methods for picking our PID parameters, and I'm actually going to look at just PI for this example, but there are values here for P, PI, and PID controllers. These two methods are both Ziegler-Nichols tuning methods. Ziegler-Nichols, my spelling is terrible. And there's one called the ultimate gain method and the process reaction method. And both of these methods are designed to be done in an actual plant setting where the system is there, the controller is there, and the system is running. And you don't have, it's assuming you don't have equations for the system. Now we do, so I'll tell you how you can also get some information from a Bode plot for these, or for the ultimate gain method. But the method in general is assuming that you don't actually have the system equations, even though you do have knowledge of the system behavior, okay? So the ultimate gain method is a method done on the closed loop system. And what it says is, you know, with the proportional controller only in your system, keep increasing the gain until you get sustained oscillations of the system. And note the gain, the ultimate gain GU that gives you that, but also note the period of these oscillations. Okay, that's the data you would take from your real system. Then you would simply look up in the table, and for our example, we're going to look at PI. To find your PI terms that fit into a controller of this form, you simply multiply or divide with your factors there, according to the table. Now, both of these methods were designed to give quarter amplitude decay responses, which means if a system is overshooting, and let me redraw that because that was terrible. If the system response to a step response would look like this. So it'd be oscillatory, where the second amplitude is a quarter of this first amplitude. Okay, so both of these methods are designed to give you an oscillatory response. If you didn't want that, you could tweak the gains. Specifically, you could reduce the proportional part of that gain, and instead of making it, you know, something like 0.45, you could make it something like 0.2 GU. And there are actual tables for this as well, but I didn't include them here. So if you're trial and erroring with your system, just try reducing that gain. Okay, so that's the ultimate gain method, and we can also get this period of oscillations and ultimate gain from our Bode plot. So let's go to MATLAB and look at a system. So these drawings. So this is the response of the system 1 over S times S plus 3 times S plus 9. Okay, and this is another important point, that this ultimate gain method can only be done on a system that has a gain margin that will go unstable if you put the gain to a certain number. So it can't be used on, you know, a first order system or a second order system. It can be used on a first order system that has dead time or delay time, or any system that whose response follows that type of response. So it can be used on a first order system with dead time, but it can't be used on a regular first order or second order system. So here we have a third order system, and we'll take a look at the gain margin for this system. So the gain margin reading off the diagram here is 50.2 dB at 5.2 radians. So we have a gain margin of 50.2 dB at an omega of 5.2 radians per second. So our GU actually would be the the non-dB'd version of this number. So 50.2 over 20, 10 to the power of that. And our PU, our period of oscillations, well, this gain margin here happens at this frequency, right? And we know that 2 pi fu is omega u. So, so the frequency is going to be omega u divided by 2 pi, and the period is going to be 1 over the frequency, which will be 2 pi over omega u. So we can find these values. And then once we have found these values, we will sub them back into the formulas here, these formulas here. So 2 ways that we could do that. In most application senses where we don't have equations for the system, we can bump the system and get it into sustained oscillations. But if we did have Bode plot data, then we could read it off Bode plot data. So we have 2 ways there. Now, for a lot of systems, they don't want you coming in and making the system be marginally stable, just on that cusp of being stable versus unstable. They don't want you to do that. So there's another method called the process reaction method, and the process reaction method is actually done on the open loop system. So basically, you are taking your measurements from like just after the controller. So you're taking the controller out of the loop and then from beyond the sensor. So actually, let me draw that here. If you had a system that has a controller, GC, the plant, GP, and this sensor H, you would actually put it into manual mode. So you could actually ignore the controller and the feedback, and you would bump the system here and measure your output here after the sensor. And so what you would get is you would give the system a little bump. The bump has to be large enough that you can measure data from it. But in a real plant, they wouldn't want you making too large of a bump. And then you would measure from the response you get. And this method assumes that the response you get can be approximated by a first order plus dead time model. So the response will have L, this dead time or delay time, and it has this time constant T. And then once you know those values, you can sub them in to the table as well. So in the, let's go back to MATLAB for a second, and I realize I showed you how to find the gains for the first system with the ultimate gain method, but I didn't show you what happened when you simulated it. So, here we could look at the graph too to find our ultimate period, right, is the distance between here. And the ultimate gain was the gain that caused the system to have this oscillation. If I simulate this system, then what I get is this response. And the time is very long because I set the time the same for all the graphs. But if I zoom in here, you can see that the original system in blue here, that was the original system with feedback, but just, you know, a gain of 1. And this was the system with the PI controller that we designed. You can see that the response is very oscillatory, but it does reach a steady state faster than the other system. So so there is an advantage there if, you know, overshoot was something that was allowed for your system. Okay, and so to go back to our process reaction method, we have a system that we've given a bump to. So this system is the open loop system that has been given the bump. And if we zoom in, we can read the delay time there, and we can read, you know, 63%. We can read the time constant here. Actually, 63%. Okay, so I will tell you right now that the time constant is 750 because that's what I set it to, and the delay is 2.5 seconds. And if you want to see that delay, I will zoom in here. And I had to make sure that my my time step was very small, otherwise MATLAB just ignored this delay. But you can see that I do actually have this time delay or dead time in the system of 2.5 seconds. Okay, so that's the open loop system. It's been given a bump, and we've read some data from that. Now, with that data, we would go back to our table here and say, okay, I'm going to design this PI controller. And now if I simulate that system, I get a response like this. And so the two things that I have here, and again, I'll zoom in a little bit. Sorry, I am just trying to zoom here. So I'll zoom in a little bit. And so the original system, I've zoomed in so much that you can't see the final value here, but it was reaching 0.5 even though I asked for a step of 1. And so you can see that with the original system alone, it doesn't have any natural integral terms. So it had this huge steady state error, and adding a PI controller allowed us to actually reach our set point and get rid of that steady state error. So right there, there's a benefit. But you notice it did mean that the system is more oscillatory with the values that we chose. The good thing is, though, look at how much faster we settle as well. So, you know, if we didn't like that much overshoot, we could reduce the gains. We would still get a decent response. And we also still have the added benefit that we have eliminated the steady state error with the P term. So these tuning rules give you a starting point based on what they've been designed to do, which is give that quarter amplitude decay response. But from there, you can tweak the values. And again, the if I just go back to the lecture notes here, the ultimate gain method requires that your system is either first order plus dead time or third order and above. It has to be a system that has a gain margin. Okay, and the process react, and it's done on the closed loop system. It's experimentally done on the closed loop system in the plant, or you can look at the open loop Bode plot. Okay. The process reaction method, you give a bump to the open loop system and look at the response and then get your data that way. And that assumes that the system is first order plus dead time, which is represented by that style of transfer function where this E term on the top is representing the dead time.